So hello everyone, this is lecture 26 for the solid state physics, and in the last lecture I have given you some questions for the homework based on the Hall effect. Okay, so these were the questions. Calculate the RH, that is Hall coefficient, for sodium metal, and the structure of sodium was given, that is BCC, and lattice constant was given, this. So how will you find? So you have the direct formula for RH, that is minus 1 upon Ne, and you need only the concentration N. So previously I have solved for the concentration many times. For sodium, inside a single unit cell, if it is BCC structure, then 2 atoms will be there and volume of cell will be A cube, and each atom carries 1 electron because of Na plus 1 valency. So total number of electrons per unit volume, that's how you can get the concentration. Just substitute it here, and you have the charge of electron. Substitute, then you will get the value of RH, that will be this, meter cube coulomb inverse. Okay, so that's how you can find. So come to the next question, that is we need to plot RH as a Hall coefficient as a function of temperature for N type and P type semiconductor. Okay, so for that you have to get some knowledge. Let me give you. So you know this expression, we write it for the semiconductor for the Hall coefficient, and just remember it always that mobility of electrons for N type material is always greater than mobility of holes. Okay, this is true for all N type and P type semiconductors. Okay, just remember this, mu h is always mu e is always greater than mu h. Okay, so when it is P type semiconductor, then when it is P type semiconductor, then concentration of P will be greater than N. It is very much greater than N as compared to mu P is less than mu N. So this term will came out to be positive for the low temperature. If temperature is low, then this term came out to be positive because mu P is less than mu N, but P is very large, greater than N. That's why we get this term as positive. So for the low temperature, we have this positive graph. Then when the temperature is moderate, then P is not that much greater than N, but P is still greater than N. It is greater than 1, this ratio. Okay, now P is greater than N and mu P is less than mu N. So these both terms will came out to be equalize each other and cancel out. So this RH tends to 0 here for the moderate temperature. That's why it came out to be here. Okay, but if we further increase the temperature for high temperature, then P is almost equal to N, the concentration becomes equal, then mu P is less than mu N, so this whole term will be negative. So graph will go like this for P type, like this. Okay, and for N type it is simple. For the very low temperature, we know that concentration of N will be greater than P and mu N is also greater than P, so this will be negative, and it is more negative for the low temperature, so it will be like here. Then as the temperature increases, P start to increase and N start to decrease, means this factor will become less negative. Okay, with increase in temperature, it is going like this, but it will never go positive here. Okay, why? Because when temperature is very high and we will say that P is almost equal to N, then still mu N is greater than mu P, and what happens, this term came out to be negative, so it will be somewhere like this. So for N type graph will be like this, and for P type graph will go like this. So just remember this will be helpful in the exams. Now today we will start a new topic, that is band theory of solid. Okay, you already have some idea of band theory, but in today's lecture we'll go in some depth. Okay, so what we will study in this, that will be classification of solid into metal, semi-metal, semiconductor and insulator on the basis of bands, energy bands. We will study Bloch function, then we will study the Croning-Penny model. This will be a very interesting topic and many questions asked from this topic. Then we will study the tight bonding approximation model. Okay, now in the Croning-Penny model we will study about the Brillouin zone, group velocity, effective mass of electron and holes, then Fermi sphere. Okay, so this will be our topics which we will cover in the following lectures. So let's say first start with the classification of solid. So you know that in the gas each atom is very far away, means they have very high thermal energy, that's why they never came into the contact. And when we start to cool them, then they will come closer, and we'll see that it came out to be liquid. And still in liquid they are still far away, means not that much that they can overlap. They are just very close to each other but not that much close. But when we further cool it liquid, then this becomes solid. And solid we see the overlaps of atoms. Okay, so this is a general idea I have given you. Let me give you a more detail. So let's say we have an atom, just consider it up to here and consider it up to here, means they are not overlapping. Okay, so this is the case. Now if you consider a single atom like this, and you will plot it, the energy and the diagram, okay, according to the distance from the center, then you will see that the energy of this electron which is at the nucleus, which will be more negative, that will be more negative. Like for hydrogen you have minus 13.6 electron volt for the single electron at the lowest energy level. Then it will start to become more positive, positive, positive. So you will get the graph like this. At the center energy will be like this, then it will go like this. Potential will vary 1 upon r. Okay, so for single atom you will get this type of curve for the energy. And you have these energy levels. Means just consider now single energy levels. This is 1s, 2s, 2p, 3s. Okay, just forget about these everything, nothing is there. Okay, so you have just single this type of a structure and these energy levels. Now for the other one, consider it up to here, so it will be like this. They all will be identical, any number of atoms can be possible here. Now when it becomes solid, so the atoms start to overlap. And what happens when they start to overlap? Means first they were having this 1s energy level, all were having 1s energy level. Now when they overlap, then these energy levels will shift because of the interaction with the electrons of the other atoms and the nucleus. So the energy levels will vary of this electron, which was first 1s, now they are overlapping, so this will affect this energy level. So now let's say the energy level shift to upwards for this first atom, and for the second atom energy levels shift to the downward. Okay, just like for this likewise for 2s energy level shift to the upward and downward, for 2p upward, downward. Now we are having two energy levels here. Just consider 2 bars here, 2 bars here, 2 bars here, 2 bars here. Okay, now there may be one more atom can be overlapping, then it will divide further. You will having more up and down, more and up and down, then it will be 3. If there were 3 atoms, then you will have 3 energy levels here. Then 4, you will have 4 energy levels. Just like if they are overlapping, then you will be having this type of many energy level, means a band of energy level, not a single energy level, it's a bands of energy level. Same for the 2s, you will have a band. For 2p you will have a band, and we can denote them like this. Okay, now each energy level have a band of energy levels, and that and energy levels inside this means the number of states will be equal to the number of atoms overlapping. Okay, so let's say n atoms are overlapping, then number of states inside a band will be n. Okay, just remember this. So let's talk about the capacity. Means we know that if it is 1s this band, if it the n atoms are overlapping and we have n states, then how many electrons can occupy inside this, how many electrons can came, the capacity of this band. So we know that 1s carries 2 electrons, it has this orbital has 2 electrons capacity, so each state will carry 2 electrons, so n states will carry 2n electrons. For the 2s band, if there are n states, then it will be 2n. For p, you know that it can carry 6 electrons, it will be 6n capacity of this and 2n for this. Okay, now we need to define. Now you understand what are bands, and these gaps means electrons can't occupy these energy levels. They will be quantized, means like this and this. So these are called the forbidden band, which can't be occupied by the electrons. So only these are possible which can be occupied. And I already discussed the capacity, and I told you what are bands and how they work. Okay, now let's see what are valence band and the conduction band here. Okay, so we have the definition. For the valence band, if band is completely filled with electrons, it's called the valence band. Means if the bands are completely filled, then we will call them the valence band. And what are the conduction band? Then if band is empty or partially filled, then that band is called the conduction band. Either it will be completely empty or it will be half filled. Okay, that should be the condition, and that is the condition to call it the conduction band. So we can understand it better by taking an example. So let's say sodium. So what are the electronic configuration of sodium? That is 1s2, 2s2, 2p6, 3s1. So if each atom carries 2 electrons in the 1s, so n will carry 2n. So the s band is completely occupied. Let's say here this band is completely occupied, and 2s2 will be completely occupied, and the p band is completely occupied. But this one, it has 1 electron per atom, so n electrons will have n states will be filled. Means n electrons will be there, and the capacity is 2n, so it will be half filled. Okay, this one. So these are completely filled, so we'll call them valence band. All are the valence bands, but this one is the conduction band because it is half filled and there are space for more electrons to flow. Okay, that's why we call it conduction band. So hope you get the idea what a conduction band. And in metal, conduction band is partially filled or empty. Okay, this is the condition I already told you. And when they are empty, then they will completely overlap with the valence band, just like in the case in the magnesium. So the valence band is overlapping with the conduction band. That's how the electron will flow inside a metal. So you know this condition. Okay, now there are semi-metal also possible. Okay, what are semi-metal? So see, this means this is conduction band and this is valence band, and this diagram is in K space. We will study more about K space in the following lectures, in next lectures. Okay, so just here take this idea that now they are maybe overlapping, but there is a difference between K axis. Okay, for the conduction and valence band. So those metals have this type of band structure. They are called the semi metal. Okay, in the normal metals they overlap like this, the conduction and the valence band. Okay, but in the semi metal they will be like this. They are on the different points in the K axis. Just remember this. I will go in little detail after when we study the K space. Okay, in the semiconductor we know that there is difference between the conduction band and the valence band, the energy gap, and this energy gap is less than 3 electron volt. Okay, and we have some examples for semiconductors, that are silicon and the germanium. For silicon we know that it is 1.12 electron volt, for germanium 0.7 electron volt. Remember these numbers, they are very important. And for the insulators we have band gap greater than 3 electron volt. So when Eg is greater than 3 electron volt, then we will call it the insulator. And for less than 3 electron volt, we'll call it semiconductor. And when they overlap, we call it metals. Okay. Example you have for semiconductor. For insulators you have diamond. Its energy gap is 7 electron volt. Now let's see the Bloch function. So you guys know about the variational principle if you studied the quantum mechanics, but if you didn't yet, then let me tell you, in the variational principle we take a trial wave function. Means what is the meaning of trial wave function? Like, you know, here is the electron. Okay, if there is single electron you can solve the Schrodinger equation. Okay, but for the more number of electrons, means more than one, then you can't solve the Schrodinger equation. because it is available only for one. So what you do for the more than one electron, you take a trial wave function to solve this. That's how the variational principle works. Now it is same in the Bloch function. Bloch function is nothing but trial wave function. So here just see this reason means here you have this potential difference very much, means it is varying with the distance. But when you see this reason, here it is plane, means for a particular time there is same potential, and you know that if potential is same, then there will be net force will be 0. Okay, means in the same potential you will not feel any force. So for this particular area the electron will be free to move. Okay, and you know that for the Schrodinger equation, means the equation of motion for the free particle is nothing but e to the power I kx. We call it plane wave function, and in this region it is called the atomic wave function. So the whole Bloch function will be product of atomic wave function and the plane wave function. Now you will say, or you will ask, that why didn't we add them, ukx and the ikx? So because it is not superimposing, means we only add functions when they are superimposing. They are different at the different reason, means it is e to the power ikx here, and it is this here, ukx here. Okay, so that's why we multiplied them, because they are at the different places. So the product of these two functions is called the Bloch function, and you can see that if at any point here the potential is Vx, that if the distance between two atoms is a, then at the same point after distance a, the potential will remain same. So this is the property you should remember for the potential and the Bloch function. So this atomic wave function will remain same, this one, ukx in the 1D. If it is in 1D, then it will be x plus a, because the linear distance a. So ukx will be equal to uk x plus a. But in 3D, then it will came out to be this, psi r equal to ukr e to the ikr, where k is, you know that kx I cap, ky j cap, kz k cap, and r is x y z. Okay. Now how can we write the condition of transitional here? Means in the 1D you see that it's after a distance it will remain same. In 3D we use translational vector, that is t. Okay, if you didn't study this, we will study about it in the crystal structure. Okay, crystal lattice. The translational vector says that it just helps to move one point to another in the 3D cases. Okay, so ukr equal to uk r plus t. So after t means one transition, it will remain same in 3D. Okay, so actually the atoms are in 3D space, that's why we take the translational vector. So this is all you need to remember about the Bloch function. Okay, so we will start the cloning panning model in the next lecture. Let's stop today's lecture here. Thank you everyone.